for this quiz, then, we just have those two reactions, SN1, SN2. So you got to find the products of that. Today, we're going to throw two more in with them, elimination reactions, and then talk about all those together. So it'll be good to get these down first. Can you see the board okay, or you want me to turn lights off? Good? Yeah, okay. Let's look at this first one then. So what are the different parts? What's the substrate here, or the alkyl halide? What type of substrate is it? Is it primary, secondary, or tertiary? Yeah, tertiary. So there's three things there. So what's the most likely mechanism right now? That we think probably SN1. What's in the leading group is bromine, and then what's the nucleophile? Right, it's going to be that whole methanol molecule. So the methanol molecule substitutes for the bromine, and then since we know that it's not going to stay with that positive formal charge on the oxygen, we have to remove that hydrogen, and so we end up with something like this. Right, so the oxygen is connected where that carbon was. So then the byproducts are hydrogen ions and bromide ions. So, be all right. Questions about that one? All right, next one. What kind of a substrate do we have here? Yeah, this is a primary substrate on the end. So what kind of a substitution is likely here? Right. So we're going to expect an SN2 reaction. What's the nucleophile? That's actually the solvent. That's going to be one of those polar aprotic solvents. Yeah, the CN is the nucleophile. We know sodium has a positive charge, so that means that CN must have a negative charge, and things with negative charges are usually good nucleophiles. So that's what we're looking at as a nucleophile here. So that means that the CN will replace the I in an SN2 reaction and be like that. And if you drew that out, like C triple bond N, that's fine too. Okay, so then C, we've got this thing. What kind of a substrate we're looking at there? Secondary. So that one can kind of go either way, right? What can help us decide if it's one versus the other? The solvent, which in this case is acetone, so how does that help us? Yeah, so acetone is more aprotic. And what about the nucleophile? How does the nucleophile help us decide? What is the nucleophile here? OH hydroxide. And how would you describe that? Is that a strong nucleophile or a weak nucleophile? Close. Strong. How do we know it's strong? Because it's negatively charged. So charged nucleophiles are going to be much stronger than neutral nucleophiles. So you got sodium with a positive charge and hydroxide with a negative charge. So the combination of strong nucleophile and aprotic solvent means that this is likely to go SN2. And so because of that, what else is special about this molecule, about this product? Anybody catch this last bit? The other thing that's special about this is the stereochemistry. This is a chiral molecule. This is a single enantiomer, which means that the SN2 reaction is going to lead to the inversion of configuration. You're going to switch the stereochemistry at that carbon that the reaction happens at because the nucleophile has to come in from the back. Remember that kind of umbrella blowing out in the wind effect? So it's flipping everything back, and that means that the OH is going to end up on a dash there. And in many cases, this is the main way that we can tell experimentally whether or not we have an SN1 or an SN2 reaction is by looking at the products and seeing if that chirality is preserved or not. If the chirality is preserved, we know an SN2 mechanism is what happened. If the chirality is lost, then it's got to be an SN1 mechanism. Okay. And then a complete mechanism for this reaction. So to do that, we have to first figure out what the reaction is going to be, if it's going to be SN1 or SN2, because those are drawn in two different ways. So how did you decide for this one? You didn't have to, but I'll be able to tell based on your mechanism. How did you know it was SN1? Because of the water, yeah. Yeah, you see that there's a secondary substrate, so it could go either way. And then you see it's a weak nucleophile and a protic solvent, so water solvent and water nucleophile. And that tells us that this is likely to be SN1. So we're going to draw the mechanism for an SN1 rather than SN2. Now, what's the first step in an SN1 reaction? Yeah, the iodine leaves. And so we end up with a carbocation right there. And then what happens? So we have some iodine here. The what? Right, the oxygen and the water comes in. Yeah, because we have a positively charged molecule here. We know we have to ultimately end up with a neutral molecule. And so the final step has to be, yeah, taking one of those hydrogens off to lead to the alcohol product. All right, good. All right, one more quiz down. So we'll hopefully have 3 more. Should be able to have 3 more. Maybe 4. All right, so where we left off last time, we've got this, we talked about the substitution reaction and the stereochemistry that's going to happen there. See you guys online?
I like pausing you.
Yeah.
I don't mean to be rude.
That's okay.
No, but I pause. Right now it's pause.
That's good. Maybe I should pause more when I'm actually talking live. So today we're going to put this all together with 2 more reactions. And then we'll really have the whole picture of what's happening with these reactions. And we'll hopefully be able to predict which one of 4 possible mechanisms these things are going to go by. So make it a little bit more involved. But to do that, first we'll just talk about that reaction in general, and then we'll look at what happens when we encounter some specific examples. Then we'll probably take a little break and then practice that a little bit and get into some of the next material. These reactions are called elimination reactions, or more correctly, I guess, beta elimination. And they actually happen with the same types of materials as, in terms of chemical materials, as the substitution reactions, which is why there's always this competition among all the different possible mechanisms. So we've got something like this. Right, a typical alkyl halide like we've been used to seeing. We treat it with let's say sodium methoxide, which we've already done, and we saw a substitution reaction. The only difference is this time we're going to heat it up. And we get a very different product. So rather than that methoxide nucleophile substituting for the bromine, we've now made an alkene. And the byproduct here, or byproducts are going to be methanol and sodium and bromide. But it's kind of strange that we've completely gotten rid of the leaving group. We haven't replaced it, but we've actually made this double bond. And that's where this name elimination comes from, or beta elimination. Another name for this reaction, which I think is kind of a mouthful, is dehydrogenation. It's a very descriptive name because it means getting rid of hydrogen and a halogen. It's dehydrogenation. And that's what's happening here. So let's look at this in a little bit more detail in its mechanism and try to figure out what's going on. So just like the SN1 and SN2, there are two possible elimination mechanisms, E1 and E2. We're going to look at E2 first because it kind of shows everything happening at the same time. So the E2 reaction, like the SN2 reaction, is one step. So everything happens at the same time. Remember SN2, the nucleophile comes in, the leaving group leaves at the same time. SN2, or that was SN2. E2, same thing. The nucleophile comes in, leaving group leaves at the same time. How that works is a little bit different. So let's draw this molecule again. But I'm also going to draw these hydrogens out. Now we know they're there. We just didn't draw them before. But they actually are important in this reaction, so we draw them out here. The nucleophile, methoxide, in the elimination reaction, attacks one of the hydrogens that is next to the carbon that the leaving group is on. And that's where this name beta elimination comes from. There's a convention in chemistry that whatever thing you're talking about, you count the carbons away from that thing based on Greek letters. So if this is the bromine, then this carbon that's connected directly to it is the alpha carbon, and then these that are another one away are the beta carbons. So alpha or beta away from a functional group, the next one would be gamma, and so on.
So wait. So is it always wherever the bromines attach?
Yeah, that's
It's going to be the
right. And then one
if
carbon
it's not
away,
bromine, then
whatever it is. Yep. So the rest of this reaction then, as this grabs the hydrogen, those electrons that used to be involved in that carbon-hydrogen bond now go down and become a double bond. So they go down and become a double bond between those two carbons. And then to make room for that double bond, we need to get rid of a leaving group. And so we see the bromine leaving. And that's what gives us that product. And that's it. That's that reaction. Okay. So now let's look at the other one, the E1 reaction, and talk about how they're a little bit similar, a little bit different. And I think it'll look pretty familiar to you compared to what we saw with SN2 and SN1. So we need a slightly different substrate for an E1 reaction. Well, I guess we don't, but we might as well because we can talk about some other stuff too. What do you think is the first thing that happens in an E1 reaction as opposed to an E2 reaction? Yeah, the leaving group's going to leave first, just like in the SN1 reaction. The leaving group leaves first, and then the other stuff happens. So we get rid of the leaving group. And we end up with a carbocation, just as before. Now we're not going to use a strong nucleophile or a strong base like we just saw, E1 reactions, like SN1 reactions, rely on weaker bases, weaker nucleophiles. So let's say we have something like methanol around. Methanol is going to act as a base in this case and take that hydrogen off. Remember that we learned that word deprotonate. It's going to take that hydrogen or deprotonate that, forming that double bond. So just like with between SN1 and SN2, E1 and E2, the effect is more or less the same. There are some variations to it. We're not really going to get into that in this class. But they basically form the same product. The difference is in how the product is formed, so whether it is a one-step or a two steps. And as with SN2, there are some stereochemical considerations with E2 that are not with E1. We're not going to get into that in this class. But if you go on and take more organic chemistry, you'll see that. Yeah.
The second arrow, like the one that's going from the bond with the H,
Mm-hmm.
that's pointing, what is it pointing to?
It's pointing to kind of the bond between the two carbons. You might also think of it as pointing right at that second carbon with the cation on it.
So it's pointing at like the plus sign.
Yeah,
Okay.
at that carbon.
Okay.
Because it's saying these electrons are now going to go connect to that carbon. Sometimes you'll see it just pointing straight at the bond. That means the same thing. So it's kind of going down to form a double bond in either case. So the nice thing about talking about E2 versus E1 is a lot of the effects, a lot of the competition between the two we've already talked about, because it really follows the same ideas as SN1 and SN2. So things that are really strong bases, really strong nucleophiles are going to favor E2. Things that are going to help stabilize a carbocation, like tertiary substrates, protic solvents, are going to favor E1. So there's really not a whole lot more to talk about in terms of elimination. There is one thing, though, that is different about elimination that we don't see with substitution, and this is true for E1 and E2. The word that we use for this, that we learned in the last chapter, is regioselectivity, which means where is the thing going. So if you notice, let's use this previous one as an example. After we deprotonate, or after the leaving group leaves, sorry, and there's a carbocation there, you have to, when you're trying to decide how the double bond is going to be formed, you need to look all around that carbon at all the possible beta carbons and the hydrogens coming off them. So in this case, there are actually 3 different beta positions, right? Everything next to that carbocation is called a beta position. So those are all potential places that a double bond could go to. So we need to look at the hydrogens on each of those to try to figure out where the product is most likely to form. So looking at those hydrogens, this is good practice for the mechanism also. Draw the alkene product that would result if each of those were deprotonated. So pick a hydrogen from each of those 3 carbons, take it off, and then put the double bond in following the mechanism from above, and see what you get. Right, I'll do the one that we already did. We'll just use the letter B for a generic base, some kind of thing. Could grab one of these hydrogens, go there, and form that. So now do that same thing with these and then with those. Let's see what you get. So how many different products are you finding? Three?
Four.
Four. All right. Which four did you find?
That's my first answer, but then I got creative.
Okay. It's usually good to get creative, but sometimes works against you. All right, let's look at these. So you got this one. And then you could also, let's say we'll do it in blue. You could also take one of these. And you could also take, I don't want to get this too messy here. Let's go around the back here. You could also take one of these. That green's a little hard to see up there, isn't it? It looks better on the paper. It's all right, you can see it. So how many different products is that?
No.
Two. Because green and red, sorry if you're colorblind, these two are the same. One is just the other one kind of flipped over. So these are the same.
Can you find the
Sure, yeah. You just have to make sure you say things like these two, you know, and don't say things like pick the green one on the exam. It's pretty common. I guess it wouldn't be that common here because it's mostly men. But yeah. So anyway, so those two are the same. This one, the blue one though, is different. And this is what was going on, by the way, in your lab last week. So Wednesday, when you got multiple products, that's why. Because you have different possible beta hydrogens that can get pulled off in this elimination reaction. So between those two, which one, how do you predict the major product? You'll remember from lab that you made some products, but there were definitely some that were much bigger peaks than the other. What makes, any idea what might make the, in this case, the red one, I'll just tell you, the red one is favored over the blue one. Any idea why that might be? Right, yeah. It's always a good guess if that comes up. So this one is favored. It's more stable. Because it's more substituted. Remember that term substituted, meaning that it has things that are not hydrogen. We talked about substituents. When we talk about substitution, in this context, we're talking about things that are not hydrogen. So this alkene has 3 carbons attached to the alkene carbons, right? 1, 2, 3. This one only has 2 and 2 hydrogens. So another way we can word that is fewer hydrogens on the alkene. So the fewer hydrogens on an alkene, the more stable it is. And there's a name for this. It's called Zaitsev's rule, named after the guy. You don't have to know that name. But you do have to know the effect of it, and this will allow you to predict the products of those elimination reactions. All right. So, that said, let's extend this a little bit more. And practice those ideas that we just talked about. Okay. Here is a molecule very similar to what we did in lab on Wednesday. Let's react this with water to make an E1 elimination. And I want you to draw all the possible elimination products and then decide which is the most favored. So use the same process. Use the mechanism, make the carbocation, and then look at all the beta hydrogens and decide which one decide which products you can make by deprotonating the various beta hydrogens. You can look back at the examples we've just done to give you an idea. That is correct. That would be a problem. Yes. step so you have 2. There is actually a third one. It's a little fine. But because it's still the same idea. Those two, yeah. Right. That one before. So you got one. No, that'd be good. Let's look at this. So it looks like a lot of you found the 2 different possibilities. So looking at this mechanistically, we lose the bromine, form the cation, and then the possible beta hydrogens here are over there and here and here. Right. So if we take off one of these, you get something like that. You can also do it over on the left, but that's the same thing, just flipped over. Everybody see that? If you take off one of these hydrogens, you have ultimately the same thing, just with the double bond over here, which is the same product. And then if we take off one of those, we get this product. So between those 2, which is going to be the more favored product? The top one, right? Because it's more substituted. And there's actually a third one that's hard to find. Anybody find a third one? The third one actually happens via the same mechanism as the blue. It's the other stereochemical product. So where this is E, this is Z. Right. That is actually a third product. And if you go back and look at what we did in lab on Wednesday and when we went through that reaction, that's what led to 3 peaks. So actually you see a lot of the E and the Z, and you just see a little bit of that other product. Between the E and the Z, what do you think is more favored? What? Yeah, it is the E. Any idea why? Yeah, that's okay. It's just, yeah, the E tends to be a little bit more stable in many cases. That's not always generally true, but in many cases it is. So those are the possible products you can form. Okay, so now we have to put all this stuff together. Because as we just saw, all of these conditions can create all of these possible products. And ultimately, it's going to be up to you on an exam to look at just a substrate and a nucleophile and a solvent and decide, is this going to be an SN1 product, SN2, E1, or E2? And so we're going to narrow that down a little bit. There's a really helpful table in your book on page 227. It's table 7.7. However, it's a little bit cluttered. So I'm going to try to streamline it a little bit in the notes to make it a little bit more easy to use. So this is SN1 versus SN2 versus E1 versus E2. So how do you tell, given just some chemicals, which of these mechanisms is going to predominate? So let's look at this. So let me put up this table so you can see what it looks like and kind of where we're going to go from it. We'll go right back to the notes. So this is what the table looks like. And you'll notice it's pretty wordy. And what I want you to focus on first is the organization. So the organization of the table is by the type of halide: methyl, primary, secondary, and tertiary. So remember, that was the first thing we always looked at when we were talking about SN1 versus SN2. It's the same thing here. We look at those first, and in some cases that answer is going to be totally clear, and we're not even going to have to give it a second thought. In other cases, it's going to be a little bit more tricky, and it could be some different possibilities. So we'll go first with some of the easier ones. And we're going to organize our table in the same way. So if you have, this barely needs to be on the table, but if you have a methyl halide, which is just CH3 with an X, so just one carbon and nothing else. There's only a handful of those possibilities. The only reaction that can possibly happen is SN2. Why do you think that is? Why can we automatically rule out all the other possible mechanisms on a substrate like that? Let's go down the list. Why can't you do SN1 on a substrate like that? What? Yeah, because it doesn't have enough other stuff attached to stabilize a cation, so it can't make a carbocation. So that rules out SN1 and E1 right there. Why can't we do E2? Why won't an E2 reaction work on a methyl halide? It is, but in this case, only SN2 can happen. So why can't E2 happen? What else do you need for an E2 reaction? What? Well, you need those beta hydrogens. And on a substrate like that, there's no beta anything. It's just one carbon. So how are you going to form a double bond if there's only one carbon? Right? So that mechanism is not going to work. All right, so that's good. That's easy. Now we can go, I mean, it's easy in that there's only one choice. All right, so what if we have a primary carbon? R is just our generic whatever carbon stuff, and then CH2, and then X. So for primary carbons, we're usually going to see SN2 reactions. It's not hindered, so things can get to that carbon fairly easily. Nucleophiles can get to it fairly easily. We know we're not going to see SN1 or E1 because they're not well stabilized by the carbocations wouldn't be stabilized. So that leaves mostly SN2. Now we can get E2 So you can get E2 on primary carbons with strong, bulky bases. Bases that take up a lot of space, that are really big molecules, will sometimes have trouble substituting. In fact, there's a whole list of molecules we won't really get into that are just known as elimination bases. They're sometimes called proton sponges. All they can really do is deprotonate things, grab hydrogens. They can't act as nucleophiles and attack carbons. So if you have those kind of special circumstances, you could see elimination on a primary carbon. So that's a possibility, but the best choice is still SN2. Okay. So now let's skip the tricky one, which is in the middle, which is secondary carbons. And let's jump all the way to the bottom to see the tertiary carbons. Right, so it's going to be R, 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 things that look like that. So these are usually going to be SN1 and E1. It's actually really difficult to discriminate between SN1 and E1. They have the exact same conditions that favor both of them, the same types of substrates, the same types of nucleophiles, the same types of solvents. So usually if you're going to get one, you're going to get the other one too. Now that's nice from a standpoint of we don't have to make that decision, but it also means that when that's a possibility, you're going to see both products. Right, so if it said something like draw major products, if you had something like this, you would draw the substitution product and the elimination product, the major elimination product, yeah, because you'd expect to get a mix. So usually this is the kind of thing you want to avoid because you're going to get this messy mix of products.
So on the test,
Yeah.
the problem, and then you give us options to circle which one it is.
Right.
Groupable.
Right. Yeah, so that'd be another option. If I gave you a bunch of choices to circle about what is the mechanism, SN1, SN2, E1, E2, you would circle SN1 and E1, unless I only gave you one product or something like that. Yeah. Yeah. The exception to this then is that, again, you can get E2 with strong, actually, it doesn't really even have to be that bulky. We'll just say strong bases. If you see a really strong base, like something with a negative charge, and you have a tertiary carbon, that tells you pretty clearly that it's going to be E2. Because you know that you're not going to do you're not going to do SN2. You're not going to have that hydroxide or something come in and substitute on that tertiary carbon. So if you see something like that with hydroxide, it has to be E2. Why does that still work? Because the elimination doesn't care if it's bulky around, if it's crowded around there or not. Because the elimination is happening one carbon away from where it's all crowded. It's just picking off that hydrogen. So that crowdedness doesn't affect it the way it does with the substitution. All right, so then the middle one is going to be more dependent on the conditions. That's where it gets a little tricky to decide. When you have something like this, and we're going to look at the nucleophile first to make our decision. So this is going to get a little tricky. But the SN2 is favored with good nucleophiles that are also weak bases. And let me give you the examples of those things so that that would be things like bromide, iodide, cyanide, things like that. And then we're going to look at what the difference is between these so you don't have to memorize a big list. because then we're going to get E2 with strong bases, like that. That is potassium tert butoxide, so it's 4 carbons and then an oxygen with a negative charge coming out of the middle. I didn't draw the potassium. That's the tert butoxide part. So notice the difference there. The stuff in the top list, other than ammonia, are all charged ions, but not oxygen, not charged oxygen, not charged nitrogen. And then the strong bases are the charged oxygen. And then this could be SN1E1. In polar protic solvents. So it could be any of the 4. SN2 is the usual answer. E2 if it's a particularly strong base. And that's our summary of all these possibilities. So a big footnote to all this. Heat favors elimination. So in all these cases, including the SN1E1 that we said they're always kind of happening, if we can heat that reaction up, we can favor the elimination. That has to do with something called entropy. I don't know if you've learned about those kinds of quantities in general chemistry, but it's the idea that creating more particles is more favored at higher temperature. And since elimination creates more separate particles and substitution has the same number, elimination is a little bit more favored at that higher temperature. So if you see something like 80 degrees or 100 degrees C, you can think that elimination is going to be more favored. If you see colder temperatures, 0, negative, whatever, that's going to favor the substitution. And so often that will be specified. All right, let's stop there and take a break. We'll come back and we'll do a bunch of practice of this, trying to figure this out, trying to look at some different possibilities.